Okay, so yeah, Jeff gave a nice overview there of the Hawk mission and a lot of the science that we're targeting. So I'll talk a little bit more about some of the retrieval side of things, in particular, how we want to combine measurements between the different instruments to do the retrievals. And then I'll talk a little bit about the testing we want to do on an upcoming aircraft campaign in the fall. So we've got these three instruments. They're all kind of looking at slightly different species. We've got far infrared from tick fire, water from show, and then aerosol from LE. And each one can do the retrieval independently. But the problem is we're always kind of assuming things about the atmosphere for different a priori assumptions. And if you assume them wrong, of course, you end up with biases in your level 2 products. So the idea here is that we can use data from one instrument or another to help fill in the unknowns about the atmosphere to improve the level 2 products with the other instruments. And so this is just kind of a rough depiction of kind of the synergy that we hope to achieve, kind of passing different parameters between the different instruments. So I'll go through a few case studies that we've looked at over the last couple years here for some of the simulation work. And the first one here was alluded to nicely by Chris Boone yesterday, where for the aerosol retrieval from LE, we have to assume the index of refraction of the aerosol particles. And in background conditions, these are typically sulfates, so they're pretty well characterized by a 75-25 mix of H2SO4 and water. But this can be pretty substantially perturbed under certain conditions. So after a large forest fire, or more recently Hungatonga, these both injected a lot of water vapor into the stratosphere, and so this 85 or 75-25 mix probably doesn't hold so well in those cases. And on the right here is just an example of a retrieval where rather than sulfates in the stratosphere, we've got water droplets. So it's kind of like a worst case scenario of what could happen here. And then if we run the retrieval with the standard sulfate assumptions, we get still a good job on extinction. There's kind of a compensating effect between the error in cross-section and the error in number density. So extinction is still okay, but the retrieved particle size starts to accrue some kind of more important errors of 20 to 30 nanometers in the effective radius. So getting the index of refraction wrong is important for that. And as Chris said yesterday, if we know both the temperature and the water vapor profile, we can just calculate the H2SO4, H2O ratio. And so then we can put that correct ratio and the correct index of refraction into the aerosol retrieval to do a better job on the LE retrieval once we know the water vapor. So that's kind of one nice synergy that we have. The second is between tick fire and LE. So tick fire, those long wavelengths are quite sensitive to the ice crystal effective diameter, which is an important parameter in the radiative forcing. But to do the retrieval, they have to assume some cloud altitude. And that impacts their retrieved particle size if they get that assumption wrong. So on the right here is that same kind of Calypso case that we've been looking at previously, where simulated tick fire retrievals are kind of the red line there, where tick fire is systematically underestimating the retrieved effective diameter due to the errors in the assumed cloud altitude. But luckily, LE, because it has dual polarization measurements, does a really good job of measuring the cloud top. So on the left panel here, this is in the kind of the gray blobs are the clouds in that Calypso scene, and then that white curve on top of them is the retrieved cloud top from LE. And you can see that the generally does a really nice job. There's a little bit of errors in the kind of far northern latitudes there where we don't have the scattering angles to pull off the cloud top retrieval, but generally it's quite nice. And so then if we put that cloud top into the tick fire retrieval, we do a better job of the rate of transfer, and then we get this blue curve here. So we've reduced the effective radius particle size bias by about a factor of 2 by doing a better job on the cloud top altitudes. As a third case, looking at the show retrievals, again, this is that same case there. So looking at a part where we, in the kind of mid-latitudes here, where we have quite a bit of cirrus clouds right up around the tropopause, and then also quite a bit of aerosol above that. So if we do just the show retrieval, this clouds and aerosols impacts the multiple scattering and the upwelling radiation. And if you don't get that right, you get some relatively large biases in the water vapor. So if you throw the LE aerosol and the LE cloud top into the show retrieval first, then you can reduce those biases. So that's what's shown here once we include the LE information. And we're still getting up to about 20% bias in the water profiles. In this case, since we're still getting the cloud optical depth wrong, which means we're still getting the upwelling radiation, some bias there. But if we also include the tick fire optical depth, as well as the ALI information, then we can do a better job of that upwelling, and we can reduce these water vapor biases down to about 2 to 3%. So including information from all three instruments really shows a real improvement in the water vapor profiles that we can retrieve. There's also some nice synergies between HAWK and the AOS mission kind of at large here. So the idea is also to fly a backscatter radar in the polar orbit, and these typically rely on a high altitude normalization in the 35 to 40 kilometer altitude range. This is a pretty clean area of the stratosphere, but there's still aerosol there. And so if you assume the wrong amount of aerosol, you'll get your calibration a little bit wrong, and that affects altitudes all the way down to the ground. So if you can characterize the aerosol at those high altitudes, you can do a better job of the LiDAR normalization and a better job of the LiDAR measurements in general. So that's one potential synergy with the AOS LiDARs. And then additionally with the backscatter LiDAR, you have to assume a ratio between the backscatter to the extinction coefficient. And typically this is something like 50 is assumed, but the variability in that can be fairly high. So this is just an example with some balloon data showing that the LiDAR ratio here is generally somewhere between 25 and 75. And because LE will be retrieving the effective radius, you can help narrow down the range of LiDAR backscatter to extinction values that you're looking at. So we're not retrieving the full particle size distribution, so you can't narrow it down to a single number, but you can definitely substantially tighten that range of values that you're looking at. So there's definitely some good synergies with the AOS LiDAR as well. So how we plan on testing this is in an upcoming ER2 campaign. So this is planned for November of this year. Ali and Show will be flown together on an ER2 aircraft. So they'll both be in a wing pod. Ali will be looking forward, and then there'll be a periscope under the wing that Ali will look out of. The ER2 is especially nice because it can fly up to about 21 kilometers. So we get a good limb view of the stratosphere at these altitudes, and we can test some of the higher altitude retrievals. The plan is to do 2 short engineering flights and then 2 longer 8-hour science flights. Likely one more continental and one more ocean, but I'll talk a little bit about that later. And then there's kind of 3 main goals for this campaign. One is to test the instruments. So LE and Show will both fly on there. There's going to be a new elegant breadboard version of LE that will fly for the first time, and then a previous version of Show that's flown on an ER2 in the past will also fly. So we'll test the instruments. That'll be goal number 1. Number 2, we've been working on the simulators for the instruments for a number of years now, doing these retrieval examples. And so we'll also be testing and characterizing these models, improving any of the biases or noise characteristics in those models so we can do a better job on the satellite simulations down the road. And then the third goal of this will be to test the retrievals themselves. So the synergistic aspects, but also just the initial level 2 products as well. So all of those components will be tested. We're targeting a few different kind of atmospheric scenarios to look at to gather the information. So we want some just general large-scale mixing phenomenon. Ideally, some areas around the subtropical jet would be nice, so we get some tropopause folds, and you get some really nice, like large-scale filaments of water vapor around those areas often. So that would be a good test of the Show water vapor retrieval and the high vertical resolution of that instrument. Convective moistening, Jeff talked a little bit about this. These overshooting plumes are kind of an important component of the water vapor in the stratosphere, but they haven't been measured that much. So this is a good test of both the science there, but also shows ability to measure above these large-scale clouds. Looking at wildfire smoke, this is a kind of a really interesting topic lately. There's been a few big fires that have injected a lot of smoke into the stratosphere. However, the microphysics of this are not well understood, I would say, especially looking into this near IR range and dual polarizations, seeing if we can discriminate between the cloud smoke clouds or the fire smoke clouds and more typical background stratospheric aerosol would be an interesting test case for LE for sure. And then lastly, we'd like to look at some thin cirrus cloud. This is kind of a lot of at the heart of the HAWK mission too, is kind of investigating the feedbacks between water, clouds, and aerosol, especially these high altitude thin cirrus ones. So this will be a main target of the campaign. And these are pretty ubiquitous out over the ocean in November when we plan to fly. So these will almost certainly get sampled pretty well. And then the last part here is the campaign validation. So this is kind of an example flight track that we could use. We're flying out of Palmdale in Southern California here. There's some ground-based facilities up in Table Mountain that do balloon sondes, so we could fly up there. In the Southern Great Plains, there's a large atmospheric research monitoring site there that has some long-wave radiation measurements that would be comparable to tick fire, as well as some more balloon sondes and an AeroNet site there. And then Houston has a MPLNet LiDAR that we could kind of give a rough comparison of some of the lower altitude aerosol that we could compare to. And then lastly, back towards Palmdale is EPCAPE, which is the Eastern Pacific Global Aerosol and Precipitation Experiment, which is hosting a large array of instruments on the ground, including some radars that would be comparable to what's flying on AOS. So we could do some comparisons with those as well. And then in addition to all of these kind of ground-based measurements, we're hoping to kind of coordinate with some of the satellite overpasses. So maybe not for this kind of overland case, but they're on the second flight or the first flight, depending on how it all works out. We would like to do a larger north-south track kind of over the ocean. And so we could ideally fly along the ground track of, say, OMPS or MLS or Calypso. So we'd be sampling the same atmospheric phenomenon of those satellites, and then we could compare against those. And then hopefully the airborne scanning microwave limb sounder could also fly on the same ER2 flight. This would provide a really good validation of the show water vapor. And so that'll get talked about in a sec here, so I won't mention too much more about that. But that's pretty much the Synergy and the ER2 campaign side of things, so I'm happy to take any questions on that.